like this was for one particular purpose: to use my authority and my age to tell you right now, shut your damn computers. Don't even bring them into the room. Yes, you too. You too.
I want to write down everything you said.
No, just listen.
John, it's being recorded. You can watch it on the
This is a rule, and what's more, any conference I am ever involved in again, this rule will be the rule. If you want to do something else, go out of the room.
No, I'm not doing something else.
John Preskill, being almost as old as I am, gets an exemption. Nobody else. All right. Let me begin with the purpose of this conference. The usual purpose of a conference is, something interesting happens, and then a conference is called in order to discuss it. The purpose of this conference is exactly the opposite. We call the conference together in order to try to make something happen. And I mean that. We're overdue, in my opinion, for a real, let's call it a paradigm shift in the subject of cosmology. Over the last 25 years, 20 years, we have developed, and when I say we, I mean a number of communities, but string theorists, quantum information people, cosmologists have discovered a large number of very powerful weapons that we simply didn't have 25 years ago. The last major change in cosmology was, of course, the development of inflation, and it's time for another one. You can't force these things, but my own feeling is it is the right time to start pushing and trying to see if collectively or individually, who knows, the paradigm is about to change. Of course, it may have already changed. Some people here may know the answers. In fact, there may be people who aren't here who know the answers. But for sure, there's no agreed upon general framework, in particular for thinking about things such as eternal inflation and so forth. No agreed upon. As I say, some people may know the answers. I know the answers, but no, I don't know the answers. Okay, if I had to guess which of the powerful or interesting tools that we've discovered over the last 25 years, which ones are almost certainly going to be part of the final story, and not necessarily the ones which will create the breakthrough, not necessarily the ones which will be the most exciting for various reasons, but the one that I think will almost certainly stick and be part of the final story. I think it's going to be the holographic principle and the complementarity of horizons. And the reason I think so is a simple empirical fact. We live in a world with horizons. Horizons set the limits on observation, not just the practical limits, but perhaps, at least seemingly, the fundamental limits, the absolute limits. However, nevertheless, that being said, we do know, in a certain sense, that there is a world out there beyond the horizon. We know this for certain. We don't need to think about fancy multiverses and landscapes to know this. Judging from the observed flatness of the universe, we know that it's at least 1,000 times bigger than the portion that we can ever see. There's a confusing situation then. Ultimate limits, apparent ultimate limits on observability, and yet we know that there's more stuff out there. How are we to think about this conflict, this tension? How are we to think about this very confusing situation? I would say there are three views of it. The first view is very unsubtle, but I think has real merits. It's unsubtle, it can't be the complete story, but I think has real merits. And it just says, accept it, swallow it. The universe is simply bigger than the portion we can see. The stuff out there is real. You can use it if it's useful to use it, and just live with it. The universe is bigger than the portion we can ever see. The second view, which I think is even more unsubtle, and which I don't think has any merit, is a kind of militant, what should we call it, militant insistence that anything which doesn't have direct observational, isn't directly observable, doesn't belong in science. A kind of I think it's called positivistic philosophy. That view, I think, is held by a large number of people, almost all of whom have constipation problems. The last view is very subtle. I apologize to some of you who may have. The last view is indeed extremely subtle. It's so subtle that I don't even really know what it is or what to call it. The only thing I know about it is that it will have to reckon with the holographic character of information. It will have to reckon with the complementary or redundant character of the two sides of a horizon. We don't know what it is yet, but at least in part, that's what we're here to talk about. Now, in looking forward, I see a number of real tensions, and I wanted to just discuss the tensions that I see, not paradoxes, not impossibilities or anything like that, but tensions. The first one, well, we have a very, very powerful tool, and we've been using it for a very long time. It's called semi-classical gravity together with ordinary quantum field theory. It works extremely well for all sorts of things. It works for elementary particles, it works for atoms, molecules, chemistry, dogs and cats and chickens and rocks. It works for the planet Earth, it works for stars, galaxies, and even the CMB. But it's definitely an approximation. And what it doesn't deal well with, is the deep questions of counting and identifying the fundamental degrees of freedom and following information. What does deal well with that is the holographic description. Whatever holographic descriptions we can imagine for the universe, at least the intent is that holographic descriptions will be good for those things. But holographic descriptions are by their very nature extremely non-local, extremely scrambled. I like the word scrambled, extremely scrambled, and therefore not at all useful for the ordinary things. As I like to say, to tell the difference between a chicken and a rock from the holographic boundary theory in ADS is completely impractical, and it's basically as difficult as decoding Hawking radiation. So we have an interesting tension between the approximate and useful and the exact. Shall I say useless? No, I don't think it's quite useless, but let me call it that. The approximate and useful versus the exact and useless for many purposes. That's an interesting tension, and it's something that we're going to have to learn to deal with. One way of trying to learn to deal with it is to learn to decode the hologram. Personally, I don't think that's the right way to go. I find much more interesting the idea that there's a missing link. And the missing link would be a formulation without chalk, because there is no chalk. No, there is chalk. I'm going to write down the basic final equations now, or at least the final diagram. The final diagram is, here is the missing link, whatever it is. And when looked at one way, perhaps, when I say looked at one way, perhaps I mean a choice of gauge. I'm not sure what I mean. But when looked at one way, one sees the local, ordinary, useful description of nature. And when looked at the other way, one manifestly sees the holographic character. I don't know what this missing link is. I am inclined to think that it's some kind of bulk gauge system with so much gauge invariance that if the gauge invariance is truly fixed, the number of degrees of freedom that's left over is holographic, but there are other ways of dealing with it where you don't completely fix the gauge, or where you fix the gauge in another way where the local properties of the system are manifest. I wish I had something more to say about this. I don't, but it's something we should definitely think about. We're very in love with holography. We're very in love with semi-classical physics. And I would say it's safe to say we don't really understand the link between them. Okay, now that's one tension that I see. Another tension that I see has to do with quantum mechanics. In particular, quantum mechanics in a situation where the observer is necessarily part of the system. It's probably useful at this point to say that what standard quantum mechanics is, it's a set of rules. And it's a set of rules whereby an observer starts a system out, does whatever is necessary to start the system out with some degree of knowledge about it, allows it to evolve without interacting with it. Be careful not to interact with it because you'll change the results, no matter how gently you interact with it. And then come back after a period of time, interact with it, and make what's called a measurement or an observation. It's a set of rules for that. They're all laid out in Dirac's book. And that's what standard quantum mechanics is. It always makes use of an external observer who is external to the system. Now, it's also a consistent framework in that it allows you to move the boundary between observed and observer. It allows you to move the boundary between the system and the apparatus, move the boundary, put Schrodinger and his cat into the experiment altogether and let Wigner watch it from the outside and so forth. So it is consistent that way. But nevertheless, the way that it's formulated, it always requires somebody on the outside of the system. And that's what quantum mechanics is. On the other hand, cosmology is a world in which there just isn't an outside. So the rules of quantum mechanics are a little bit unclear. It raises the question, how do we think about things such as, from the inside, how do we think about things such as probabilities in a situation where we get at most one observation of something? Maybe it only happens once, or at best we get one observation. We can also think of all sorts of things. We can only see the Big Bang once. What does it mean to use probability? That's something that I think, we tend to dismiss as, okay, philosophy, but I think it's going to come back and bite us at some point. How do we think about the collapse of the wave function in a situation where there's nothing out there to become entangled with? Decoherence and entanglement are the same thing in my view, entanglement with an external system. If there is no external system, how do we think about that? How do we think about correlation functions on distance scales larger than the horizon? These things are all mysterious. To quote a famous philosopher whose name I just learned, his name was, I always thought it was Bishop Berkeley, but that was a California version of it. It's Bishop Berkeley, isn't it? If a quantum tree falls in a quantum forest and there's no observer to observe it, does anything happen? That, I think, is a serious thing that we're going to have to deal with. Maybe not, but yes, I do think so. The last of the major conflicts, not conflicts, but tensions that I see, you all know, many of you have worked on it, and it's something very puzzling, the so-called measure problem. We need a measure. We can't do without a measure. Without a measure, everything is equally probable, and if everything is equally probable, science obviously just descends into chaos. And yet, despite our best efforts, there are no agreed upon, and I emphasize the word agreed upon because, again, somebody here may be right, but nobody else agrees with him. Well, that's the way things happen. I mean, Feynman went to give his talk about Feynman diagrams, and everybody thought it was complete crock. He was right, of course. It may be that somebody here does have the right idea, but there are no agreed upon fundamental principles. I don't mean phenomenological principles, I don't mean guesses, I mean fundamental starting point which gives rise to a measure. So that is the third of the big problems that I see that we should be talking about. And then, of course, there's the fourth big problem we should be talking about, and I don't know what it is. Okay, so, no, I mean that. I mean, we don't know what it is. Are all these problems connected? Yeah, I think they must all be connected. They all have to do with information and its limits. One of the reasons that I wanted to bring people together here was because I think that information theorists do have a lot to offer us. At least in one case that I know of, quantum information theorists, one of whom is sitting here, another of whom will be here later, have added something truly remarkable in my mind to our ideas about what horizons are and how they work. And I'm, of course, talking about the work of John Preskill and Patrick Hayden on black holes as mirrors. Does that work imply that cosmic horizons are mirrors? Well, we don't know, but this, again, is something that I think we need to talk about. Let's see. I was going, it's almost the end of my time. Is that right, Rob? I can't see my watch very good. I have this very expensive watch that I bought for $10 and I can't see it very well. So there it is. It's 9:30, but I had intended to talk a little bit about the measure problem a little more. Do you want to go on or shall I stop? I started late. All right. So I did want to talk about the measure problem, not really my own work, not the work of anybody around me, but just to, I wanted to say things in the simplest possible way that I could about a collection of different measure proposals, none of which I think are infinitely well motivated, but some of which I think have some real merit to them, and we need to see if we can understand. Okay, so let me the view of the measure problem that I'm going to take is one that other people here have pioneered, namely the idea of a cutoff in time. And let me just outline a framework for thinking about it. Everybody from Stanford knows about this. We've talked about it ad infinitum, but it's a nice, simple way to think about the problem. And so I'll talk about it just for about 10 minutes, maybe.
By that time, ad infinitum.
You should let us sit together. Let me tell you, it's much worse when he and I sit together. All right, so here's the idea. There's a multiverse out there, right? I'm going to plot vertically time, and I'm going to plot proper time. Now, proper time in what frame? Einstein frame, string frame? This is a little bit of a problem, but let's suppose, let's take it to be Einstein frame. Okay. Now, we draw a cutoff surface. Where the cutoff surface is doesn't matter. We can just label it by definition t equals 0. We draw the cutoff surface, and anything below the cutoff surface we count, anything above the cutoff surface we don't count. All right, now, what I'm interested in, this could be just pure de Sitter space, but we're interested in bubble nucleation. So let's draw and stick a bubble into this. And I'm going to make a very simple approximation to the bubble. It's just a square, and just a square, and it looks like that. And in that bubble, observers conform, and we're interested in the probability. Let's give this a Hubble constant h. Let's give this a Hubble constant small h. And we're interested in some sense in the measure for the quantity small h. Okay. Now, let's also assume that when the cutoff surface passes through the bubble, the rule is, I don't know what the rule is, but let's make a rule that the cutoff surface goes somewheres. It may jump, it may not jump in proper time. It may even go down. All right? What we're going to do is we're going to try to count observations. Let's not talk about observers. Observers is too anthropomorphic. Let's talk about observations. Is that any less anthropic? I don't know. If the observation takes place below the cutoff surface, we count it. If it takes place above the cutoff surface, we don't count it. And what we're going to do is we're going to integrate over the nucleation point, both in space and time, T nucleation, X nucleation, and construct a measure by asking how much forevolume is there in which you capture observers inside this region here. How much forevolume is there for this particular bubble, where, assuming that you do capture observers. Now, the first thing is this. When you integrate over the time of this here, because the integrals are all exponential, they're dominated by the endpoint. What is the endpoint? The endpoint is when the cutoff surface up here is hard against the observers. Where do the observers occur? Let's assume, or observations, let's assume that observations occur, roughly speaking, after a time t0, t observer. Observations occur after, in our world, after roughly 5 billion to 10 billion years, and they last for another 50 billion years, and then everything is gone. So t0 is several tens of billions of years in our world. It could be different in other worlds. Okay, now, what is the measure, or what is the forevolume or the volume occupied by this particular setup? Well, we have to integrate over the nucleation time, basically. We have to integrate over the nucleation time and the nucleation position. And the integral over the nucleation position is just going to be the volume of the surface, whatever it happens to be, at time t nucleation. That volume is going to be of order e, is it minus or plus? E to the 3h t nucleation. That's the scale factor cubed, the scale factor of the inflating de Sitter space, e to the 3htn. That's the amount of volume that's swept out given that observers occur under the cutoff. Okay, next thing. What do we choose? What is our rule? Let's call that the measure. It's just a 3 volume that we pick up when we integrate over space. Okay, next rule is, what do we take for this, for the jump in the cutoff surface? Let's try some examples. The first example is to say nothing happens to the cutoff surface. And this is called the proper time cutoff surface, or the proper time cutoff. Let's suppose that nothing happens. Then this distance here, by definition, is t0. And you can see that t0 and tn are the same thing. Not quite. Tn is minus t0 because tn is negative. Okay? So we can rewrite this as e to the minus 3h t observer. That's it. That's the measure for the proper time measure. Now, unfortunately, it doesn't even depend on little h. It depends on big H, but assume big H is given. Big H is some ancestor vacuum with a large Hubble constant. And T0 is the amount of time that it takes to create an observer. What is this a probability for? Let's assume it's not a probability for big H. That's assumed to be large. We can think of it as a probability for T0. How long does it take for an observer to form? Any incredibly unlikely event which makes it easier and faster for an observer to evolve will be vastly favored. Let's say we can do something to evolution to increase the speed of evolution by 1 second. This is an enormously suppressed factor, and so we will get a huge advantage by speeding up evolution by 1 second. That's called the Youngness Paradox. It's the Youngness Paradox, and it's the main reason why this is rejected. I think it's good enough reason to reject it. Let me show you how to think about some other measures that are popular. All of the other measures that are popular and that seem to have some virtue to them are based on what I'm going to call Stanford's principle, or Stanford's rule. This has nothing to do with Stanford University. It has to do with Douglas Stanford. Douglas, where are you? There's Douglas. Douglas is a student at Stanford, and he first articulated this rule. What it says, let's draw it over here. What it says is that there is a quantity. We'll choose that quantity in different ways, but let's call it Q. And it's an extensive quantity, meaning to say that it's an integral over space. And the rule is that when the bubble intervenes and chops out a region of the ancestor vacuum, it chops out a bit of Q, but the rule is you have to put back the same amount of Q in the cutoff surface inside the bubble. What is Q? Well, you get to choose. You get to play some games. So let me show you some games. The first Q is volume, ordinary volume. Let's try that. Let's start with volume V0. This distance here is T0, and this is T nucleation over here. Okay? So let's see if we can calculate the measure. Given that the volume is conserved, so we call it the volume is conserved. That's Douglas's rule. Let's try it out and see how it works. Okay, so the volume that you excise, the volume that you chop out, this is T equals 0. The volume that you chop out, it started as V0, but it exponentially expanded. Now, we're talking about now the expansion as seen from the outside. The amount of volume that's chopped away is going to be V0 times E, I think, to the minus 3 Tn. That's it. That's how much volume is chopped out. How much volume do you put back? The amount of volume that you put back is governed by the expansion rate in the bubble. It's governed by little h. Right? So the volume that you put back, we could call this the excised volume. The put-back volume, volume excised, volume put back, that's equal to V0 times e to the plus, sorry, there's an h here, capital H here, e to the plus 3 little h times T0. That's the time between here and here. Okay? Let's set those equal. What will we find? We will find that e to the plus 3 htn, that's the measure, is given by e to the minus 3 h T0. To me, that's a magical formula. It's an incredible formula. What it says is that the probability will tend to cluster. Think of it as a joint probability for small h and T0. What it says is the probability will tend to cluster at a time and a Hubble constant whose product are order 1. This is a true fact about our world. The Hubble constant of our world and the time that it takes to make an observer are about the same, the Hubble time. This is the mysterious conspiracy, what's it called, the coincidence problem. I find this a very dramatic fact, or a very dramatic conclusion. This measure is called the scale factor cutoff measure. I'm not even going to try to remember who the authors are. You probably know who the authors are, but it'll confuse me to death to remember 4 authors simultaneously. One of them is here. Maybe, oh, no. At least 2 of them are here. At least 2 of them are here. Sorry. Sorry, I forgot about you, Alex. Okay. So this measure is, to my mind, very interesting. I don't know where the first place that this formula appeared. Certainly the names of Busso and his collaborators, Freivogel, are connected with it. It may have appeared first in the papers of Guth and collaborators, but I'm not sure. But this is striking. This is very striking. There are prefactors that people put in here. There are all sorts of details, gastrophysics and everything else determines prefactors. I would be inclined to say, just ignore them. We don't know in detail how to compute these things. Let me try another definition for Q. Instead of taking volume, and volume, of course, depends on what metric you're using. Einstein, string, it's not invariant. So this doesn't sound like a really good invariant thing. Let's try something else. Let's try the number of Hubble volumes that are either in here or in here. The number of Hubble volumes are conserved. Why the number of Hubble volumes? Well, it's a nice geometric quantity. It doesn't depend on your choice of definition of coordinates and so forth. Just the number of Hubble volumes. Oh, it depends on how you slice. Yeah. But it doesn't depend on whether you're using Einstein metric let's try. We'll slice in this very artificial and simplistic square bubble approximation. We'll just slice horizontally. But at least it doesn't depend on rescaling the metric. Okay, so what does that mean? That means instead of Vxized, we should take the number of Hubble volumes. And the number of Hubble volumes is simply the volume divided by the volume of a Hubble region. That means multiply by h cubed. In other words, instead of volume excised equals volume put back, we multiply it by h cubed. H cubed. The only effect of that is to include an additional factor here, which is of the form capital H cubed over little h cubed. Now, what I'm interested in is comparing different values of little h for a fixed value of big H. So the big H dependence here is just an overall factor. It'll go into the normalization of normalizing my probability distribution. But what I'm interested in is the little h dependence. Now you'll notice that it still has the marvelous feature of having a big bump of some sort roughly at the same place, but it's much more singular at small h and tends to push you even more towards small h, maybe too much towards small h. But otherwise, it's pretty similar. This measure has a name also. It's the light cone time cutoff measure. It's also due to 4 particular people, several of whom I think are here. How many people are involved here? I know Ben is, and a whole bunch of you are also here. This is the light cone time, and it's characterized in my language by saying the thing that you put back and that you take out is number of Hubble volumes. Let me give you one last example, which I'm fond of, which was in fact suggested a good deal later than either of these by other considerations, by myself, Steve, and Douglas Stanford. And we call it the information measure. The information measure says there's no good reason to be counting Hubble volumes. You should count bits of information. You should count number of degrees of freedom. That's very simple. Every Hubble volume has an amount of entropy or amount of hidden information in it, which is the area of that Hubble volume. Okay? That means you take this quantity and divide it by h squared. And it just gives you another example where instead of h cubed downstairs, it's just one factor of h. It's softer at small h, not as extreme at small h. But I think the point is, number one, this is interesting and exciting. It's interesting and exciting that there's a certain amount of robustness to this factor here. But the other fact is that there's no principle that's telling us what to do. There's no principle in particular singling out one of these things from another. There's not even any principle telling us that the extremely bad, I'm having a senior moment. The extremely bad proper time measure should be thrown out. So it's exciting, but we really don't know what we're doing, and that is what the purpose of this conference is, this little workshop. Thank you, and let's let the birth pangs begin.
term of things